Hi everyone, this is a lecture on section 9.3, the second part, part 2, and all I want to do in this part is to give another example of the usage of Cielo's first, second, and third theorems by classifying all up to isomorphism. So let's classify up to isomorphism all groups of order 21, which is equal to 3 times 7. So we did this before, but I want to do it again because it goes much simpler now that we have all this machinery behind us with Cielo's theorems. Okay, so we'll show that, the abelian, by the fundamental theorem of finite abelian groups. G would be isomorphic to Z3 cross Z7, which is isomorphic to Z21. It's cyclic of order 21. Okay, so that's the only abelian one. Non-abelian, okay, we'll show that G is equal to or isomorphic to, depending on what you call these elements, the group generated by X and Y, such that X has order 3, Y has order, or X has order 7, Y has order 3, and then Yx is equal to X squared Y. Okay. So that's what we're looking for here. It's going to be isomorphic to that. So there's only two groups of order 7. There is the cyclic one, and there's this thing. This is what's something known as a Frobenius group. So kind of like dihedral groups of order p times q for special types of p and q. Those are like the dihedral groups, which are ordered not p times q, but 2 times p, right? Where q is equal to 2. Anyway, so there's only two groups of order 2p. There's the cyclic one of order 2p and the dihedral group of order 2p, and this is kind of similar to that. Okay, so first, so by Cielo's first theorem, there is A and B subgroups of G such that the order of A is equal to 7, right? And that's prime, so it's got to be cyclic. So say A is generated by little a, and so that's the Cielo 7 subgroup. It's got order 7. And subgroup of order B, subgroup B of order 3, say B is generated by little b. All right, so A is order 7, little a is order 7, little b is order 7. Okay, it can't be that both A and B are normal. It cannot be that both A and B are normal, because then, right, because then we get the following. order of A intersection B, right, is going to have order 1. The order is going to be a divisor of right. It's a sub A intersection B is a subgroup of A, so its order divides 3. And it's also a subgroup of B, so its order divides 7, or the other way around. Subgroup of B, so its order divides 3. Subgroup of A, so its order divides 7. But there is no common divisor except 1. So the actual intersection of A and B is just the identity. A times B is going to be equal to all of G because the order of G is equal to 21, and the order of A times B is order A, order B over order A intersection B, which is 7 times 3 over 1 is 21. Right, so the intersection of A and B is the identity, and the product of A and B is all of G. So if A is a normal subgroup of G and B is a normal subgroup of G, then G is isomorphic, then by section 9.1, G is isomorphic to A cross B, right, which is isomorphic to Z7 times Z3, which is abelian. Right, a contradiction. We were saying it's not. A contradiction. So we're saying it's non-abelian. So one of them is not normal. Either the ClO3 subgroup or the ClO7 subgroup. Okay? The number of ClO3 subgroups, right, is congruent to 1 mod 3, right, and divides, right, 3 times 7 equals 21. Well, it actually has to divide 7, right, because anything that's 1 mod 3 doesn't divide 3, so it has to divide 7. So the possibilities are, well, things that are equal to 1 mod 3 is 1, 4, right, and then 7. Alright, so, well, 4 doesn't divide 7, so these are the possibilities, 1 and 7. The number of ClO7 subgroups is congruent to 1 mod 7 and divides 3 times 7 is 21. So it has to divide 3. So the only possibility is 1. Is 1, right? So A is a normal subgroup of G, but B is not. So the ClO7 subgroup okay. So A is a normal subgroup of G, and B, the ClO3 subgroup, is not normal. And there's going to be 7 ClO3 subgroups. Okay? All right. So, again, however, the order of the product, AB, of the two subgroups is going to be equal to order A, order B over order A intersection B. So that's going to be 3 times, or the other way around, 7 times 3 over, well, the intersection is going to be 1, again, because A intersection B is a subgroup of A, and it's a subgroup of B, so its order has to be a common divisor of 3 and 7, which is 1. Is 21. So AB equals all of G. So A and B, so little a, is equal to the set generated by all products of little a and little b. Right, so G is generated by little a and little b. But the b is not normal, so you can't do that direct product thing that you do in section 9.1. And as a matter of fact, you don't want to. Since which one was normal? A, the CELO 7 subgroup was normal. Since A, which is generated by that little a, right, B times A, right, is going to be equal to A to the K times B for some K. Okay? Which values of K work? Which values of K work? All right, well, not K equal to 0 because otherwise BA is equal to B. Contradiction. B is equal to B, so A is equal to 1, a contradiction. A contradiction because the order of A is 7. The order of the identity is not. Not K equal to 1 because then and AB equal to BA means G is abelian, which it's not. So not K equal to 0, not K equal to 1. Okay, so it's K equal to 2, 3, 4, 5, or 6. Okay, well, which one's it going to be? Okay, so BA is A to the K B. So now so A has order 7. Yeah, so now B, now this, so B inverse is A to the K. All right. Now, so we're going to use this. B to the third, A, B to the minus 3 is just equal to A because B to the third is equal to 1. B to the third is the identity. So you can do this here. So B squared, B inverse, B to the minus 2 is equal to A. Well, let me see, how should I do this? A is B to the third. Let's do it this way. So A is equal to B inverse times B squared on the left, B to the minus 2 on the right. But this is A to the K, right? Is A to the K. So that's B squared, A to the K, B to the minus 2. But this is equal to B squared, A, B to the minus 2, that whole thing to the K. Right? It's that old thing that X, Y, X inverse to the N is X, Y to the N, X inverse. You remember that? We proved way back in section 7.2, 7.1 or something like that at this conjugation relationship, xy, x inverse to the n is xy to the n, x inverse. So that's exactly what we've got here, right? I got b squared a to the k, b squared inverse, and I just factor out that exponent. All right. But this is equal to, so do this trick again, peel off a b. B a, b inverse, that whole job there to the k. All right, but this is a to the k again. Inside there to the k. Bringing that k outside to the k, right, that's just k squared. Right, when you have these nested exponents, you multiply them. Right, but that's a to the k again. So that's a to the k to the third. Right? So we conjugated by b 3 times, right? Right, so a is a to the k to the third. So a equals a to the k to the third. So since the order of a is 7, right, k to the third is congruent to 1 mod 7. Okay, so let's check it out. K to the third mod 7. So I got k mod 7, k to the third mod 7. Not 0 and 1, right? So 2. So 2 to the third is 8. Mod 7 is 1. 3 to the third is 27. Mod 7, that's 6. 21, 6 will remainder 6. 4, 16, mod 7 is 2. 2 times 4 is 8. So that's 1 again. 5, so 5 is minus 2 to the third. So that's minus 8 to the third. So that's minus 1 to the third is minus 1, which is 6. That's 6 mod 7. And 6, which, go away. 6, which is minus 1. Minus 1. Minus 1 to the third is minus 1. Minus 1 is 6. So that's 6 mod 7 again. So k is equal to 2 or 4. Right? So if k is equal to 2, then G is generated by A and B, where the order of A is 7, the order of B is 3, and BA is A squared B. Right, and that's what we wanted. Where is it? Right, that's what we wanted. There it is. Right. G is isomorphic to the group generated by x and y, where x is order 7, y is order 3, and yx is x squared y. Right? That's what we were looking for. And that's what we got. Except for calling them A and B. Alright, so in this case, G was generated by A and B, where the order of A is 7, the order of B is 3, and BA is A squared B. So as required. And then what if K is 4? So if K is equal to 4, then let C equal B squared. Now, right, A, which is generated, well, now, C, subgroup generated by C, is the same as a subgroup generated by B, is B. Right, so G, which is equal to generated by AB, is also generated by AC. And CAC inverse is B b squared, a b to the minus 2, is b inverse, but this was a to the 4th. Right, so that's equal to b inverse to the 4th. This is a to the 4th again, a to the 4th to the 4th, so that's a to the 16th, which is a squared. Right, so CAC inverse is equal to a squared, so CA is a squared C. So G is generated by A and C, where order of A is 7, order of C is 3, and CA is A squared C, as required. Same group. So whether or not that K was 2 or 4 in the BAB inverse is A squared, or BAB inverse is A to the 4th, if BAB inverse is A to the 4th, then you just replace B with C, and you get the same thing again. So that's it. That's all for groups of order 21. So in this course thus far, we have classified all groups up to order 16. We didn't do 16. No, so we didn't do 12 either. The grad students will be doing order 12. I'll let them think about that. But you know, we've gotten pretty far here in classifying finite groups. So we did everything up to 21 except for 16 and 12. And you know, and beyond that. Okay, so anyway, so that's the lecture on section 9.3, second part.